This is an example of reflection at normal incidence. So in free space, z less than or equal to 0, a plane wave with a magnetic field given by this is incident normally on a lossless medium, and the medium is described by these parameters here, permittivity and permeability, in region z greater than or equal to 0. So the interface is at the plane z equals 0. Determine the reflected wave HR, ER, and the transmitted wave HT, ET. All right, so the first thing you'll notice here is that we're given the magnetic field. Usually we work in terms of the electric field, so it might not hurt, it might not be necessary, but let's first get the incident electric field. So to do that, we'll notice that we're in free space here. Okay, so free space, so the intrinsic impedance is this eta 0, and that's 120 pi approximately. Okay, and so now we will say that the incident electric field is equal to, we're going to take our HI, which is 10 cosine of this guy, and we're just going to multiply it by eta 0. And we can do that because eta 0 is purely real, so it does not introduce any sort of phase shift between the electric field and the magnetic field. So that is to say, we can just take 10 times eta 0 times cosine of 10 to the 8th t minus beta z. Okay, and I'm going to leave off the direction for right now. And you'll see that H was in milliamps per meter, and so when we multiply by eta 0, this is going to give us millivolts per meter. And I've left off the direction on purpose, so we need to figure out the direction of this thing. So this is going from, or I guess this is moving towards positive z direction. You can see, so the variation here is positive z. Another way of noticing that is not from H, but from the definition of the interface. So we're in z is less than 0, and then we transmit to z is greater than 0. So this thing must be moving in the positive z direction. Okay, and so if you notice then that the magnetic field points in the x direction, we ask ourselves, well, how or what is the direction of the electric field? And remember that the direction of the electric field, so a unit vector in the direction of the electric field, cross a unit vector in the direction of the magnetic field, must equal a unit vector that's in the direction of propagation. So we've already said then that the magnetic field is in the direction of x, right, ax, and the direction of propagation is in the z direction. So what must be here? What's the direction of the electric field? And so you'll think about the right-hand rule. So here's z, here's y, here's x. So we know, well, we've got an x and a z. We know that E is going to have to be positive or negative y. And so you can try both, but the answer is going to be negative y. And so just to illustrate that, imagine pointing your fingers of your right hand down the negative y-axis. So you can do this right now. Point in the negative y-axis, then curl your fingers towards the x-axis. So I'm pointing right now, even though you can't see my fingers, I'm pointing to the left. And then I curl my fingers out of the screen towards me, and then my thumb is left pointing in the z direction. So that's exactly what we have. So this must be negative y. Again, so you point in the negative y direction, curl your fingers towards the positive x direction, and your thumb is left pointing in the z direction. So that is all to say that we're going to put a negative there and a y there. So that is the incident electric field. Okay, so now let's talk about the transmission and the reflection coefficients. So we've got eta 0, which is actually eta 1, meaning that's the first material that this wave transmits, or not transmits, but is incident in, right? And then we're going to find eta 2, right? And so remember our definition of eta was j omega times mu, so I'll put mu 2 there, divided by sigma, and I'll put 2, plus j omega epsilon 2. Okay, so remember we've got a lossless medium, right? So sigma is 0, and then we're given epsilon and mu. And so if we compute all of that, we see that that is actually 2 times mu 0 over epsilon 0, which is to say it's 2 times eta 0. In other words, 240 pi, like that. Okay, so what does that give us? Well, that gives us gamma, the reflection coefficient, is 2 times n0, not n0, excuse me, eta 0, minus eta 0 over 2 times eta 0 plus eta 0, or 1/3. And it also gives us the transmission coefficient, which is 2 times eta 0 divided by 2 eta 0 plus eta 0, which is 4/3. Okay, so now we have those coefficients. So let's talk about transmission, and let's get beta first. So if you remember, and I don't expect you to remember this, but you'll want to have this on your notes or bunny-eared in your book. Beta was defined like this. So I'll just write the expression down. 1 plus sigma over omega epsilon square root plus 1, right? Okay, so if we plug in, so we're trying to find beta of the wave here, and so if we plug in the frequency is 10 to the 8th omega, right? And mu, right? Mu is 8 mu 0, and epsilon is 2 epsilon 0, and sigma is 0. What we find is that this is 4/3. Okay, we're talking about transmission right now. Transmission. So we're using the transmission medium. That is to say, we're using these parameters here, not those of free space. So we get 4/3. Okay, and that would be in radians per meter. 4/3 radians per meter. All right, so then we recall that the transmitted electric field is just going to be 4/3, which is the transmission coefficient, times the incident electric field. And the reason that's the case is because this is purely real, the transmission coefficient, that is. Purely real, so there's no phase change or anything like that, so we can just multiply it in, and we're going to get negative 40/3 eta 0 cosine of 10 to the 8th t minus 4/3 z, right? Because we found beta in the y direction. That's millivolts per meter. Or if you like, if you plug in n0 is 120 pi, this gives you negative 1.6 pi cosine of 10 to the 8 t minus 4/3 z in the y direction, volts per meter, if you factor out the 10 to the, or if you bring in the 10 to the minus third. Okay, so that is our transmitted electric field. Good. So how do we get the transmitted magnetic field then? HT. Well, what we can do is just divide by eta 2, right? So again, because eta 2 is purely real, we can just factor that in. There's no phase change, so I'm going to take the 40/3. I'm leaving off the negative for a second, and I'll explain that in a little bit. But we're going to take the 40/3 eta 0, then divide by the eta, the intrinsic impedance of the second medium, right? Twice eta 0 cosine of 10 to the 8th t minus 4/3 z. And then I'm going to leave off the direction for right now, and this would be milliamps per meter because this 40 thirds up here was in millivolts per meter. Now we need to think about the direction. So the transmission is still in the z direction, positive z direction. E is negative y, so needs to be H needs to be positive x. Okay, so I'm just going to put positive x there, and that's why I dropped the negative here. Again, so you can point your fingers of your right hand down negative y because that was the electric field. Curl your fingers in the direction of H, which is what we're saying is positive x, and then it should point to the positive z direction, which is the direction of propagation, and it does. So now we're good with that. And you can cancel out the n zeros and so forth, and do a little simplification there. Okay, so now let us talk about the reflection, the reflected wave. So I'm going to erase the transmitted wave. Feel free to pause the video if you need to. Okay, but let's talk about the reflection. So the first thing we need is beta, and unfortunately I erased the equation for beta, but you need the frequency, which then the frequency is 10 to the 8th, and you need the permittivity and the permeability, and this is of free space now because the reflected wave is still in free space. So what you end up getting is 10 to the 8th from the frequency times the square root of mu 0 epsilon 0, and that is 1/3. Okay, so the electric field then that's reflected is negative 10/3. I'll talk about the negative 10 in a second. Negative 10/3 eta 0 cosine of 10 to the 8th t plus 1/3 z in the y direction millivolts per meter. So let me explain why this is a plus now and where this negative came from. So we're talking about the reflected electric field. So the electric field then must be traveling in the opposite direction. So that wave that was going in the positive z direction, so we had minus beta z, is now going in the negative z direction because it was reflected. So this becomes positive beta z, positive 1/3 z. But we were always assuming that the electric field points in the same direction after reflection. So that negative stays there, right where it's at, negative 10. And then where did the 1/3 come from? The 1/3 is due to the reflection coefficient. So what we did was we took the reflection coefficient and we multiplied it by the incident electric field, and that gave us a reflected electric field once we changed minus z to plus z. Okay, so then I can bring in the eta 0 and so forth is 120 pi, and I can write this if I want as negative 0.4 times pi times the cosine of 10 to the 8th t plus 1/3 z in the y direction, and that's if I bring in the 10 to the 3rd. So that's now in volts per meter. That's the reflected electric field. And then how about that reflected magnetic field? Well, now that I've got the electric field, then remember that I can divide by the intrinsic impedance. So actually when I do that, if I look up here, before I boxed it, I had negative 10/3 times the intrinsic impedance. So if I divide that, then the intrinsic impedance drops out, and I'm left with negative 10/3 cosine 10 to the 8th t plus 1/3 z, and I'm going to come back to the direction in a second, but this would be in milliamps per meter because this guy, which we're looking at right here, is in millivolts per meter. Okay, and when I divide by eta 0, then that becomes amps instead of volts. So now we need to ask ourselves about the direction of the magnetic field. So I know that the reflected wave is going like this. It's moving in the negative z direction, right? I guess let's look up here. So the reflected wave is going this way. Okay, so that is to say AK now is negative az, and and the electric field points in the negative y direction. Okay, so what about our magnetic field? Well, that has to be negative AX. And it is. So we've got the negative there, so we'll tack on AX. If you're uncertain about that, a way of double checking is, again, point your fingers in the direction of the electric field. So we're talking about reflection. So the electric field is negative AY. So I would point my fingers to the left. I'm doing that right now, actually. And then I'm going to curl my fingers in the direction of what we're saying is the magnetic field. So we're saying that is negative AX. So if I'm pointing my fingers in negative AY and I have to curl them to negative AX, which goes into the screen, I actually have to flip my thumb down, curl my fingers into the screen, and my thumb is pointing down, which is the direction of propagation, right? Propagating in the negative Z direction. So we know now that we have that correct.